In this session, we're going to see about composition of functions. If we consider a function to be like a machine, this is called a machine diagram. Say we have a function f into which we're going to put an input x. Well, the output is f of x according to our function notation. Composition of functions would be the effect of stringing together more than one of these machines. So suppose we have another function g, and we take the output from f of x, and put it into g. Now, looking at the function notation, when we put x into f, we got f of x. So now, when I put f of x into g, I'm going to get g of f of x. That's how we're going to write that down. Notationally speaking, this is denoted using g and a little circle f of x, and this is called composition, and we would say g little circle f out loud as g composed with f of x, and the meaning of it is g of f of x. We would actually have, in most cases, a different output if we were to change the order of the composition. In other words, if we take x and put it into g first, then that output is what we would call g of x. If we then take that and put it into f subsequent to that, then our result would be f of g of x. And that would be denoted f little circle g of x. As kind of a concrete way to look at how the order of composition of functions matters, suppose you have a coupon for some store that gives you 5% off of your purchase. And then you have another coupon that gives you $10 off of your purchase, and for some reason they let you use both of these things. You can play with some numbers if you like. You would actually get a different ultimate sale price depending on whether you use the $10 off first or the 5% off first. So the order of composition matters, and it's just a matter of which rule is going to get used first. To illustrate this, of course, we have some examples. Let f of x equal 1/2 x plus 3 and g of x equal x squared minus 1. We're asked to find in part A f composed with g of -2. And what that means we're going to do is find f of g of -2. So let me get some colors going on here. I'm denoting f using blue and g using red. And so first what we need is g of -2. Right? We're looking at f of g of -2. As it turns out, g of -2 is equal to -2 squared minus 1, right? So that result is going to be 3. Now what we're going to do is we're going to take that 3 and put it into f. So g of -2 is going to replace, there's going to be replaced by 3. F of 3 says to take 1/2 of 3 and add 3 to it. I know, fractions, it's okay. So here we have 3/2 plus 3, and I at this point think of this as 3/2 plus 6/2, you know, common denominators. And so we get 9/2 as an output there. Next we're going to look at g composed with f of -2. Same input, but we're reversing the order. And so again, this is going to be written as g of f of -2, for which we first need to find f of -2. So f of -2 is what we get when we take 1/2 of -2 and then add 3 to it. So that's going to be -1 plus 3, and so 2. Now we're going to take that 2 and put it into g. So g of 2 is equal to 2 squared minus 1, and so 3. So the outputs are different. There's not a way that you can look and see what it would be if you flipped it around. You just have to apply the appropriate rule first. Next, we're asked for f of 1 and g of 3, two separate things. For reference, I'm going to rewrite the original functions. And to find f composed with f of 1, we're looking at f of 1. And so we're going to take the number 1 and put it into f. And we're going to get 1/2 times 1 plus 3. And so I again 1/2 plus 6/2 is equal to 7/2. And then we're going to take that 7/2 and put it again into f, because this was f of 1. And so that's going to be 1/2 of 7/2 plus 3. I don't like it any more than you do. 7/4 plus 3. And again, 7/4 plus, I'm thinking of 3 as 12/4. It's going to give me 19/4. Finally, why don't you do g of 3, like pause the video. Okay. So g composed with g of 3 is g of 3, which means we're going to put 3 inside of g. And so that's going to be 3 squared minus 1, so 8. And then take that 8 and put it again into g, because we had the same letter twice. We're using the same rule twice. That's going to be 8 squared minus 1 for an answer of 63. In these cases, we were looking for one, particular function values for these compositions, and 2, we were using the rule, the expression. In our next example, we're going to see how to do this using a graph. So here we have directions: use the graphs of f and g to find f composed with g of -2 and g composed with f of -2. I should label these. The blue linear graph is f, and the red parabola is g. And no, you don't get to arbitrarily name functions like that, but I do. So we're looking at f composed with g of -2, which means we need f of g of -2. And so somehow I need to figure out what g of -2 is. Using the graph, that means I'm going to look at the x value of -2 and see what the red parabola's function value is there. Looks like the answer is 3. So here I've got that g of -2 is equal to 3, and so 3 is going to replace g of -2 in the expression f of g of -2. Now for f of 3, what I need is f's value at 3. And so the linear value, or the value of the linear function, when x is 3, is, looks like 4.5. These are actually the same functions that we just saw, but these are the graphs of them. In any case now, the answer here is 4.5, and I really wouldn't care if you used 4.5, 9/2, or 4.5. Next, we're going to switch it around again, and we're looking at g composed with f of -2, which means we want g of f of -2. And so, looking at the function value at -2 for f, the linear function, that output is 2. So we can say that f of -2 is equal to 2, which means that g of f of -2 now becomes g of 2. And so I need the function value of g when x is 2, and the parabola has a value of 3. And so the answer here is going to be 3. Next, we are asked to find f composed with g and g composed with f and their domains for various functions. And in our first such example, we are given that f of x is equal to 1 over x plus 1, and g of x is equal to 3x plus 6. First, we're going to find f composed with g, which is f of g of x. And notice this, we weren't specified f of g of 2 or anything like that. We're just going to be finding the expression that indicates the result of the composition. F of g of x is what happens when we put g inside of f. So continuing on with the same kind of color coding I'm using blue for f and red for g. The rule for f of x is 1 over x plus 1. The argument now is g of x, so we're actually writing 1 over g of x plus 1. For this, we need the rule for g, and so we're actually going to write 1 over 3x plus 6 plus 1. And that simplifies to 1 over 3x plus 7. Now for the domain. When we are looking at f of g of x, for any particular value, which we aren't doing right now, but generally speaking, the input goes first into g and then into f. And so in terms of that machine diagram, we have g first and then f. And so whatever inputs we have first go into g, which means I need to concern myself with the domain of g. Then we get an output. That output goes into f. And that's what we write as f of g of x. I then need to look at the domain of the output, f of g of x. In this case, what we see, since the answer is 1 over 3x plus 7, is that the domain is going to be the set of x such that x does not equal negative 7/3. That's for the output function, right, our result. When we look at what the domain of g was, since it was linear, 3x plus 6, we don't have any additional restrictions, and so that's going to be the answer to the domain. Next, we're going to reverse the order of the composition. Keep the functions for reference. Last we found f of g of x, and this time we're going to find g composed with f of x, which is also written as g of f of x. And so what that means is we're going to take the rule for f and put it into g. G says to take 3 times the input plus 6. And so 3 times f of x plus 6. So for us, what that means is 3 times 1 over x plus 1 plus 6. And if we can only simplify this a little bit, 3 over x plus 1 plus 6 is going to be the result there. And so in this case, we see that in the result, we have x plus 1 in the denominator. So x cannot equal negative 1. We can't have that zeroing out. And then again, considering g of f of x as a machine diagram picture, we'd be taking an input and first putting it into f, and then taking that result and putting it into g, and that's how we get g of f of x. And so I need to consider the domain of f. As it turns out, since f is 1 over x plus 1, we don't pick up any additional domain restrictions. It's just the case that the composition is 3 over x plus 1 plus 6, and the domain of the composition is the set of x such that x does not equal negative 1, right? We just can't zero out a denominator. Next, same instructions. Our functions are f of x is equal to the square root of x minus 3, and g of x is equal to x squared. So for first, f composed with g, some people say fog and goff, I don't know, man. F composed with g, that's f of g of x, which means we're going to take the rule for g and put it into f, where we see x, which means in this case we're going to have x squared minus 3 inside of a square root, so the square root of x squared minus 3. As far as the domain, x would first go into g, right? And then the result goes into f for any particular value. And so we first need to consider the domain of g. Since g of x is x squared, the domain is all real numbers. We don't really need to worry about that. For the result, we have the square root of x squared minus 3. And so what we need are numbers that when we square them, they aren't less than 3, right? In other words, we need x squared minus 3 to be at least 0, greater than or equal to 0. There's something called a quadratic inequality, which is a topic unto itself, but if we just kind of reason our way through this, we can probably figure out a domain here. If we consider a number line with values like -1, -2, 1, and 2, and 0, of course, then it seems to me that 0 squared minus 3 is negative, 1 squared minus 3 is negative, likewise -1 squared. When we start to get like -2 squared and 2 squared, then we have values that, x squared minus 3 is going to be positive. As it turns out, and this should kind of make sense, the kind of cutoff value is going to be the square root of 3 and negative square root of 3. As long as our numbers are bigger in magnitude than the square root of 3, we're going to be good to go. So it actually turns out that the domain of this function is going to be the interval from -infinity to negative square root of 3 together with square root of 3 to infinity. And, square brackets at the endpoints there, because we are allowed to have the function value equals 0. Next, we're looking at g composed with f. Well, let me circle this as the answer. Now, g of f of x says to take the rule for f of x, which is the square root of x minus 3, and put it inside of g, and so square that result. That's going to give us x minus 3, which at first blush seems to have a domain of all real numbers. But we need to keep in mind that any values that we are evaluating need to first go into f, which means that we need to consider the domain of f, and the domain of f is 3 to infinity, because f is the square root of x minus 3. So, the domain of this composition of functions is the set of x such that x is greater than or equal to 3. I would also accept the interval notation of 3 to infinity. The last example of this type is we have f of x is equal to 3 over x, and g of x is equal to x over x plus 2. First, f composed with g, so f of g of x, says that we're going to take the rule for g and put it inside of f. And so 3 over x is f. G is x over x plus 2, and I'm now dividing 3 by the fraction x over x plus 2, which means we're going to flip and multiply. So 3 times x plus 2 over x, which I'm going to write as 3 times the quantity of x plus 2, divided by x. Now again, machine diagram picture. First a value would go into g, and then that value would go into f, and that result would be f of g of x. Which means we need to consider the domain of g. The domain of g is the set of x such that x is not equal to -2, because g is x over x plus 2. Then we need to consider the result. For the result, the domain would be the set of x such that x is not equal to 0, because the result has a denominator of x. For the whole composition, the domain has to exclude all the values that had to be excluded before. So, the set of x such that x does not equal -2 because of the first function that any value would go into, or 0 because that's what we pick up when we have the resulting function. So here's the function and its domain. Next we're going to find g of f of x. G's rule is, if I reference that, x over x plus 2. And so I'm going to kind of write it down as blank over blank plus 2. And then we're putting f into that. F has the rule 3 over x. So we're looking at 3 over x over 3 over x plus 2. This is a complex fraction, which I've been trained to simplify on sight. And I'm going to do so by multiplying the numerator and denominator by x. In the numerator, the factor of x divides out, and I'm left with 3. In the denominator, for the first term, the factor of x divides out, I'm left with 3. In the second term, the 2 picks up a factor of x, and so I have 3 over 3 plus 2x. I'm sure that we know that we cannot cross out those 3's because you can't divide out terms. Now we consider the domain. First, the domain of f. Since f is equal to 3 over x, I know that x cannot be equal to 0. For the resulting function, since the denominator is 3 plus 2x, I know that x cannot equal negative 3 halves. So the domain of this is all of the numbers that we didn't already exclude. The set of x such that x does not equal negative 3 halves or 0. Next, we are asked to express a function uppercase f, or f as I like to say it, as f equals f composed with g. And the function that we have is f of x is equal to the square root of 2x plus 1. In other words, envision this function, the square root of 2x plus 1, as an outer function and an inner function. The outer function we're going to call f, the inner function we're going to call g. And I know that because this says f composed with g, and that's the order that is given to us. And hopefully you can see that the outer function in the square root of 2x plus 1 is the square root function. And the inner function is simply the argument of that, 2x plus 1. And so what we're going to say is that f of x is equal to the square root of x, and g of x is equal to 2x plus 1. We have now decomposed this function, and it's a skill that would be useful down the road in a future math class. It's also just part of understanding function composition. I do want to make a note and say, don't really do anything like say that g of x is equal to x. We always want to make sure that the function that we are writing down is, let's say, an interesting function, if you will. Finally, we have 3 functions. F of x is equal to the square root of x, g of x is equal to 3x plus 1, and h of x is equal to x squared. We are asked to find a composition f composed with g composed with h. So, if we let f be denoted using blue, g with red, h with yellow, then what we're looking for is blue composed with red composed with yellow, if you will. In other words, I'm going to take f of x, but I'm going to put g of x inside of it, and h of x inside of g of x. So starting from like the outside in, let's say, f of x is the outer function, f of x is the square root function, so I'm going to draw a big square root. G of x is 3x plus 1, so I'm going to write that down as 3 times something plus 1. And then h of x is the something, so x squared. So ultimately what we have is the square root of 3x squared plus 1. That's it. Now we aren't asked to find the domain in this case, but if we were, again, looking at this from a machine diagram standpoint, any particular input value would first go into h, and then into g, and then into f, and that output value would be f of g of h of x. Because x is going into h first, I would need to consider the domain of h. Once that's done, I would then need to consider the domain of the output. In other words, when we're considering domains, we never have to worry about the intermediate functions directly. It gets taken care of by considering the domain of the first and the domain of the result.